me show you how to be a good breezy and change your predictions.
Maybe for, your future work, like, what do you see as the most exciting trends or advancements in your field? And also, where do you see the future of probabilistic programming heading? Because of course you work a lot on Stan. You also work on some Python now, thanks to Osvaldo being there with you. Like spreading the dark energy of the Python world. Thanks, Osvaldo. So basically, I'm curious to know where your head is at here, where your future projects are.
Mm-hmm. Yeah, I think there's a lot that excites me about our research agenda at Alto, but also others. What excites me in our group is that, and the people that we work with more generally, is that we're still very actively thinking about how can we set priors about things that we have expert knowledge on. Summary statistics, something about the predictive space, and what do these prior imply then for all of these coefficients that we have in the model, where we typically just go ahead and set normal 0-1 priors. That is still under active development. So we have like let's say the simple time series stuff covered to some degree, but there's so much more to be done in time series, even with multivariate models. So there are ways to define this R-squared step also for multivariate time series stuff. I think that's really cool and has a lot of policy applications as well. Because central banks and so on who do the econ policy for a country, they often know that everything is related to each other.
Mm-hmm.
If you're modeling inflation, you're also going to model GDP and so on and so forth. And doing this jointly is really the way to go in the end. And these priors, I think, can also be very good for those kind of questions.
Mm-hmm. Mm-hmm. Yeah.
And
no, for sure. Like in the end, kind of everything is a vector autoregressive model.
I mean, you're preaching to the choir, but I would tend to agree, like at least approximately.
Yeah. I mean, like if you basically, but often the limitation is the computational bottleneck, right? But honestly, almost all the time you would want vector autoregressive processes on the observation equation and on the latent state equations. Like most of the time, you have correlations everywhere, and you wanna estimate that. The problem is that we often don't do that because it's just impossible to fit. But ideally, would be able to do that.
Yeah, exactly. And a lot to be done there still. And we're also looking a lot into still. Workflow in terms of how, prior is one thing, but a whole new aspect also is model selection. So we're also very excited about a project where we're investigating the question of when is selection necessary if you have different priors to fulfill your goal in terms of prediction in the first case scenario. But even for causal analysis, this is an important question. How do you set the priors, and do you need selection to somehow produce reasonable predictions for the treated versus non-treated? And when you have lots of covariates or other structure in your model, so we're working also on that. I think there's going to be fun results going to come out of that.
What do you mean by selection here? Selection processes, selection bias, or?
More like a variable selection or like component selection. Okay. Yeah, so that there's some stuff like this predictive inference, which does selection based on can you find a surrogate model which gets as close as possible to a full model, like a Gaussian process that is hard to compute. And like statistical folklore tells you that if things get too hard, as in you have too many components, do selection. Because then you implicitly decrease the variance of your predictions because you're focusing only on a couple things of your model. And what we're kind of saying is, that's not necessarily true if you have good priors. And understanding when that statement in fact is true and when it is not so true is an interesting question, because like let's say in those causal analyses where you have randomized controlled trials, let's say a drug is being administered to one population randomly or not, then does it make sense to let's say use an R-square prior, which implicitly will say the treatment effect is correlated with other parameters that you're estimating, and is that a good choice? And what we're saying is like it depends, and we kind of go into detail about when R-square priors and priors like that are good, and when they're bad, and when selection is needed and when not.
Nice, yeah, super interesting. Let me know when you have something out on that. I'll be very interested to read about that and maybe talk to you again about that, because that sounds very very important and interesting. So yeah. I'll be very curious about that.
Maybe one thing about other people's work, I was very selfish talking about our work, but I think there's some really cool stuff I'm excited about that comes out from groups around like Paul Berkner and so on, which are also picking up work on normalizing flows and amortized Bayesian inference. I think that stuff is going to be really good going forward, because you can simplify computations, you can reuse models for huge estimation tasks. I think this will make the kind of general Bayesian computational workflow much more easier in the future. So I think kind of using this, maybe integrating it with like the knowledge that we're working on, also how to model, and then how to do computation. Those things, they're interdependent. And I think for the future, I'll be very excited to see what comes out of that.
Yeah. Completely agree with that, and I'll refer listeners to episode 107 with Marvin Schmidt about amortized Bayesian inference. That was super interesting, and haven't been able to use that in production yet, but really I'm looking forward to be able to do that and like have an excuse and a use case for that, because this looks really cool, and yeah, I completely agree with you that it has a lot of potential for that, and yeah, everything Marvin and the Baseflow team and Paul Berkner are doing on that front, and like even anything Paul is doing is just like always super brilliant and interesting. And what I love is very practical. It's not research that's like, okay, that's cool, but I can't even do that because the math is too complicated and it's not implemented anywhere. That's always his research, and you guys' research at Alto is what I really like. Is like it's always geared towards practical application and not just, okay, that's cool math, but nobody knows how to implement that. So that's really cool, and well done on that. I think it's amazing. And talking about normalizing flows, I'll also add to the show notes NutPy from Adrian Zebolt. So he was also on the podcast. I will also link to his podcast episode with me, where he came and talked about zero-sum normal and NutPy, which is an implementation of HMC, but in Rust, so that's much faster. And now he did something very cool in NutPy, and you can use that with PyMC and Stan, models. But now you can use normalizing flows to adapt HMC in NutPy. So basically what this will do is first run normalizing flow and train a neural network with that, and then once it learns the way to basically turn the posterior space into a standard normal, then it will use that to initialize HMC and run HMC in your model. And so, of course, you don't want to do that on a simple linear regression, right? It's just overkill, because it's going to take like at least 10 minutes to fit, because you have to train a neural network first to learn the transformation of the posterior space that would make it a standard normal. But if you have very complex models with very complex posterior space, so things like Niels funnels, banana shapes and so on, where it's very hard to find a reparameterization that's efficient, then trying the normalizing flow adaptation of NutPy could be very interesting to you. And literally, if that works in your case, it can make your MCMC sampling much faster and also much more efficient. So that means much bigger effective sample size. So I will definitely do that in the show notes because I think it's something people need to know about, and we'll try it out, and that way Adrian can know this is working out there in the world, and I know he loves that. So. Awesome. Well, David, that's cool. Anything you want to add that maybe I didn't ask you or mention before I ask you the last two questions?
I don't know. I mean, I think we covered a lot of ground here. I think there's a lot of cool stuff here. It's probably impossible to find it all. I do want to make an honorable mention to all this work that goes into prior elicitation. I know that you're also interested in that, Alex. But there's also work that is coming out of Helsinki and Aalto, which is looking into how can we go from knowledge about effects of covariates to priors. And we have tools that can go for work for simple cases very well. But what if you have correlated effects? Like, let's say, I don't know, age and income predicting, I don't know, school outcomes or whatever, right? Those things are often highly correlated, and then going from like a conditional expectation on predictions to the prior. So let's say you have this age and this income, but how does that relate to education outcomes? And specifying the prior in that way, I think, is super interesting. And there's a lot of cool stuff also being developed that helps to specify these priors with then, artificial intelligence, like, AI trying to kind of go from, a very prose and conversational way of talking about then what we want to do a prior on to then actually implementing it in things like Stan and PyMC and so on. I think that's a lot of the future that's awaiting people who are maybe not so interested in learning Stan and details, but still want to do cool Bayesian inference, and then these kinds of things I think will make it accessible to a much wider audience than it is right now.
Yeah. I mean, definitely. I mean, even for us, who are like power users of the software, that would make my model workflow be way faster. Because most of the time, that's a much, much more interpretable and intuitive way of defining the priors than, trying to understand what the prior on the AR squared process of my time series, of my structural time series model is going to mean. Like, the only way I can understand what this means right now is just doing a cumbersome iterative process of changing one knot at a time and seeing how that impacts the prior predictive checks, and maybe an interesting metric, like the prior squared or something like that. But like, that's the only thing that's really reliable right now, and it feels like it can be automated for sure, because it's like a lot of cumbersome back and forth, basically, where probably something AI assisted would make faster.
Yeah. But still, it's kind of nice that you still have to get your hands dirty in a way. Like, not everything is too automated, because it does let you learn a lot. But the problem still remains that not everybody has the time, inclination, or interest in getting their hands that dirty.
Yeah. No, and also, like, everything has a trade-off, right? So the time you spend on that is not time you're spending thinking about expanding your model, making it more expressive, and so on. So, if we can make that easier, that'd definitely be amazing, and a high impact. Awesome. So I need to let you go, David. That's already like 1 hour and a half we're recording, so I don't want to take too much of your time. You'll come back on the show for future work you have, future